and I am your host, Dr. Matthew Richardson, and welcome to another stream of CosmoQuest Astro Office Hours. Um, before we jump into before we continue the problem we've been working for over the past two streams, let me go ahead and verify that I'm actually streaming on Twitch. So just give me a quick moment. Let's see. And not seeing anything just quite yet. Let's wait, see what we get. Yes, we are live for about now a little bit underneath a minute. All right, so let me first go ahead and do what I typically do now, which is completely exit Chrome, boot it back up again, go back to Twitch. Okay, now it's showing that we're live, and hopefully, yes, I have access to the chat. Let's pop that out. Pop out. And we can continue. So, just to quickly make sure that everything's working with the chat. Hi all. All right, that wasn't what was expected. Let's try it again. Ah, there we go. All right. So now I can also type to you guys in chat. All right. So we left off with almost nearing the end of our problem, and then I ran into something that I didn't expect. That is that the math like it was going to be a little bit off. And so after reviewing what I had did before that point, which is what's currently on the screen right now, I realized that the way in which I calculated the scalar curvature was not correct. Well, not that it wasn't completely correct. I left some terms off. So, and the reason why I left those terms off is because in trying to calculate the Einstein tensor, G sub mu nu, I knew that I only had to be concerned with the 0, 0 component of that tensor, which would correspond to only needing to be concerned with, well, for the most part, being concerned with the 0, 0 term of the Ricci curvature tensor. However, the scalar tensor requires that I evaluate all non-zero terms of the Ricci curvature tensor. Whereas the Einstein tensor would only require me to evaluate the 0, 0 component of it as far as the equation goes, or what's readily available to be seen within the equation. So I'm going to scroll back up top, and we're going to go back here. This statement is not right, so I'm going to have to make modifications to it. So let me go ahead and find it. Term 4, blah, blah, blah. Here we go. And so the first two parts of the equation are right. R equals the contravariant metric G superscript mu nu times the covariant Ricci tensor R sub mu nu. That's good. However, the latter two parts are wrong, or slightly off by a few terms. So the G superscript 0, 0 times R subscript 0, 0 is good, but I have to add on 3 more terms to this. So I'm going to make the modification here. Just increase the font so you can see what I'm typing here. Can you guys hear and see me? Just want to make sure. Typically, I see like the chat and people are saying hi to everyone, and I'm not seeing that right now. So let me make sure that everything's actually working as it should work. Just take a little quick pause here. I'm going to open up so let me do something else really quick. Testing. All right, I can see my comments. And so because I can see my comments, I'm going to assume that just no one hasn't put a comment. All right, let's continue, guys. So if you guys are actually typing things to me, I can't see it. Which is not good, actually. So let me see if I can make sure that. Let's see. Oh, I see. So Larry's letting me know that something appears to be going wrong with the chat. And the example he uses that he typed something and it just disappeared. So there's a black hole in the chat right now, guys. So let me unfortunately that kind of sucks. So it's not just me. Okay. So I apologize then for what's going on here. But I also now just realized that I just jumped into a bunch of math right now, and I'm not actually explaining what I'm doing, and just in case that there's actually like new people here, you'd want to know what I'm doing here. So a few streams ago, Larry asked a very simple question, and it was all related to Newton's law of gravity, and that is if one or both masses, um, if one of two masses is moving relativistically, will the fact that that mass is moving relativistically change the gravitational force of attraction between those two masses? Answer is yes, and relativity says that it should. And so Newton's law would not be a good approximation. Okay, chat appears to be working now. Thanks, Susie. Um, so if you guys are still typing things in chat, I can't see it. So let me do this. I'm going to go ahead and exit Chrome again. I'm just going to reboot everything for Chrome and see if the chat is now going to work for me. But yeah, the short answer, of course, is going to be yes, or no. No to the fact that Newton's law of gravity will not be a good way of solving for the force of attraction between the two masses if one of the masses is moving relativistically. So we went ahead and started a much simpler problem than trying to figure out what the force is between two masses if one or both of them are moving relativistically. And we're basically just going to derive the gravitational potential of one mass in the case if the mass is at rest. And we're using general relativity to do so. And so we've done a lot of calculations um, here in these past two streams. And so we were nearing the end of the problem, and I ended up noticing that one thing looked off. And so as I went through the math again, I realized, oh man, I made a mistake with calculating the scalar curvature. I only considered the 0, 0 term of it, where I should consider all the non-zero terms of this particular variable. And so the scalar curvature is dependent upon, well, one, the metric, and two, the Ricci curvature tensor. And so let me go ahead and see if I'm going to get chat now. I'll pop it back out. Everything's loaded back up here. Okay. Well, if all of you guys can talk to one another, that's great. At least through chat, that is. I can't see chat still. I want to continue, and hopefully we can use Slack as a means of being able to. Wait, you log in and log out. It works. So, that's the one thing I didn't do. I didn't log out. So let me try that. All I did was reboot Chrome. Let's try logging out and logging back in and see if that helps. All right, so I'm going to log out. I'm logged out. I'm going to log back in. I'm using my own personal account versus using CosmoQuest's. Oh man. Just give me 1 second, guys. I'm trying to quickly log back in. All right, I'm logged back in. I'm happy I remembered my password for this, for Twitch. All right, CosmoQuest. We're back on. Let's see if we get the chat back. All right, I'm sorry, guys. My chat just appears to just not want to work today. For those of you who have access to the Weekly Space Hangout Cruise Slack, if you wouldn't mind just sending your messages through there for now. And I'm just going to go ahead and continue, and I'm going to periodically check that. All right, so determine the Ricci curvature, the scalar curvature is off by a few terms. So we need to solve for what those terms are. And what I was doing here was I was modifying it to account for the terms we're missing. There should be 4 in total. 1, 1, 2, 2, 3, 3. So these are the terms that we're missing. The metric in this case, as we've defined in the previous streams, is going to be a diagonal matrix. So we only need to be concerned with the diagonal elements of the Ricci curvature tensor as well, because everything else will be 0. All right, so these are the terms we have to solve for, and I actually started to do it myself. Started sometime this morning, and let me pull up that information. We've already went through the math, which is up above right here. All the math for the 0, 0 component of the Ricci curvature tensor. But now we need to do all the other elements, or at least these other 3. R sub 1, 1, R sub 2, 2, and R sub 3, 3. Okay, so I need to open up another scene to do this. So let's just duplicate. This will make things easier. And I'm I'm going to, if I do that, if I remove that, that's not going to be good. So I can't actually duplicate this. Let's delete this. So I'm going to go to scene 1, and I'm going to open up some new stuff here. So let's see if it has it there. Extra math. So let me just quickly get some of this set up here. And lastly, we need to also have the corresponding PDF that goes along with this. And I promise we're going to get right back into the math in just a second, just after I quickly, there we go. And so what we're seeing in this document that I'm loading up here on the screen is the extra bit of math that's going to be required to solve this problem. All right. And this is going to basically solve for all the other terms. And I wanted to see if I could find like a really quick way of doing this. And honestly, I couldn't. I mean, I've already solved for all the Christoffel symbols. So it's just a matter of plugging and chugging and seeing which terms cancel out, which terms survive. But nevertheless, the process is still very tedious. So let's go ahead and do it. Let's get it done. All right, so Tanner's also saying that he's having issues as well. Huh. Yeah, I'm not Twitch Prime neither. So I wonder if you know Twitch is like letting us know something here, like their Twitch Prime members are important to them, which is completely understandable. But we should be important too. We should be able to see the chat. But I don't think that's the case. I think it's just it's something. It's probably something else. It's more likely something else. All right. So I've already solved for term 1 for the 1 component of the Ricci curvature tensor. Term 2 is solved for. Term 3 should also be. All the terms should be solved for. So now it's just a matter of getting the simplified form for it. And note, this has to be done for each term, each component along the diagonal of the Ricci curvature tensor. A lot of this is reminding me of the reason why I didn't miss doing the math from General Relativity. So I want to put everything together. So let's just copy and paste this. And let's see if I can, or actually, let's do this, no indent. So subtracting term, and I think it's term 4 from term 3. But yeah, this is what it's about. For some of the problems that you work with, you can use summation notation and just like know exactly like what terms won't survive and stuff like that and figure it out. But I just couldn't see any other way other than just, you know, physically writing everything out. And there's also that issue of me kind of not remembering some of that stuff. If I look at at summation notation, I can read it and be like, okay, I understand what's going on here. Let's see. All right. So for these terms, actually it's 3 and 4. So I'm actually just taking this and I'm subtracting from that this, which is the fourth term. And so that's going to be leaving me with all the rest of this. So where is it? Right here. So I could just copy this. Let's see what happens, what it looks like. Am I getting all the terms here? 1, 2, 3. Am I missing anything? 1, 2, 3, 4. 1, 2, 3. I think I'm getting everything. At least I hope I'm getting everything. Just to verify, let me just scroll up and look. 1, 2, 3. I'm missing the 0. Is that it? Actually, some of this stuff is being truncated. I don't have that much space to work with. Maybe I should do this so we can see everything. Okay, that made it worse. Kind of, sort of. Let's see. And that made it no better. Well, slightly, it made it slightly better. The key thing is that everything can be seen. That's what I really want. I want to happen here. All right. So one of the terms is missing, but that term is equal to 0 anyway. So far so good. And honestly, guys, I wish I just knew the answer, and I would just say, hey, the curvature scalar is equal to this. Let's just go from there. But I honestly don't know the answer to that. I know what the end result should look like, which is the reason why I know what sort of modifications may need to be made along the way. Which is why there was the issue when in the previous stream I was like, this isn't going to come out to what the end result should look like. So there must be a problem, and I found one of those. I found what I hope to be the single problem, and now we're going to go ahead and fix it. It's weird. A piece of hair is on my face here. All right, so this is good so far. I need to also subtract now the other term. All the information we're currently seeing with all the parentheses and stuff like that, this is all strictly the first term. This is gamma superscript rho subscript rho lambda times gamma superscript lambda subscript 1 1. So now we have to incorporate the other term. And I'm just going to try to make modifications because I don't want to keep adding too much stuff to this. Or maybe I should actually. That might be the better way of doing this. So the next term is going to be minus. Now I need to make all the appropriate modifications. Okay, let's see, minus and dash quad. And I pray and hope that it doesn't truncate stuff. And it is. So what I'm going to do is I'm going to get rid of all the zeros. And that should free up some space. The zeros are unimportant. And one last zero. I think we still need the plus sign here. All right. And hopefully this makes it a little bit better. And I think it did. Okay. So good plus. I need to make sure that everything has the appropriate sign. So starting where that first negative sign is at, I need to modify every single positive sign or every sign after that to be the opposite. So this needs to be a negative sign here, negative sign here, negative sign, negative sign, negative, and negative. And also here as well. Because the second, so all the elements of the second term need to be negative. All right. So now that we have this, we can go ahead and we can find what the simplified form is by seeing what terms cancel out. And guys, this is what graduate school is kind of like. At least when you're doing the coursework portion of it all. Looking at equations and stuff and writing out so many terms. And then probably coming to the realization that a lot of those terms either cancel out or equal zero. And it's frustrating because if you get a sign wrong or if you miss the cancellation of some terms, it can throw. Well, if you miss the cancellation of a term, then you'll probably end up running into it eventually. But the signs are important. Signs are so important. So keeping track of all that is crucial. All right. I'm going to go ahead and check Slack for a little bit here and see what's going on. Hey Tom. All right. So there's several in the chat who aren't prime. It's back. So it keeps going. It keeps coming and going. I see. Yeah, I'm still not seeing anything for chat for me. I'm going to try this one more time because I want to be able to communicate with you guys. Because honestly, that's what makes all of this fun. Because me just sitting up here talking is it's cool, but it's better when there's like a little bit of dialogue. All right. See if Twitch has fixed itself. Okay. I'm able to see me typing. If someone else could type something, even if it just says like testing, I want to see if it works. For a brief moment there, I did see a comment by Peter in the Twitch chat. All right. I can see everyone's chat, typing now. Hey, Tom. Hey, Susie. And hi, Peter. Alright, so that means I probably can also see who else is here. Hello, Electrical Skateboard. Hello, Tchaikovsky. And hello, Uncle Bill Druin. Guys, welcome. Oh, wait, this is a new person. Hello, Herlayu. That's an interesting name. Welcome. We are having a little bit of fun with General Relativity. Oh, well, hi, Tanner. Alright. So, right now what we need to do is cancel out some terms, guys. And this is the part that can be very, like I said, tricky. Because it's easy to miss stuff. Alright, so this very first term. So, I'm going to ignore the fact, of course, the 1/2 they repeat with every single, which is actually 1/4 for each term. That repeats. So I'm not even going to pay attention to that. But I'm going to look at the subscripts here. So this term is the 100,111 term, and it's negative for this case. So let me see if it repeats itself anywhere else. One zero zero one one one. I got 100,100. I'm not seeing it. But then again, let me make sure I've copied everything over. Yeah, I've copied everything over. All right. That term survives. Next thing is to look at all the other terms now. So we got 200,211. I am not seeing that one. It actually might be easier if I start with these negative terms and then compare them to the positive terms, because there are a lot fewer of these. So 100,100, and it's going to be positive in total. Does that repeat itself? Not that I can tell. 122,211. I don't see that one. 311, 311. It's the exact same term. Okay. Oh, it repeats itself. I'm seeing it again. So I see it here, and I wish I could highlight this stuff. Is there a way to highlight this stuff? Or better yet, I can zoom in on it. And you guys can see the zoomed version of it. All right. So this is what I mean by like signs are important and also stuff can repeat itself. So I see it here. So 311, 311. And then it repeats itself again right there. 311, 311. In this case, the term itself is going to be positive. So the term itself is going to be positive. In the uppercase, it is negative. So that term cancels out. So I can just erase that, or those two terms. Of course, I got to find it in all of this stuff that looks like code at the bottom of the screen, but it can be done. Let's see. I think I see it here. Is this the third term? It's the third term on the third line. So first line, second line, third line. Is it this? No, it's the second term of the second line. It's this one. Um, so this goes away. And then on the next, it's 1, 2, 3, 4, 5, 6. On the sixth line, it's the last term. So 1, 2, 3, 1, 2, 3, 4, 5, 6. So it's here. And it's going to be this term, which now goes away. And there we have it. We've gotten rid of one term. Many more to go. And so basically what you'd want to do is you'd want to continue this process for every single Ricci scalar, or I'm getting the words mixed up here, but you get the point. You have to repeat this, and it's a lot to do. It's easy to lose track of stuff, especially when it's like all typed out like this. End up deleting the wrong thing, but we're going to get it done though. So 0, 0, 1, 1. I kind of know what the solution would need to be in order for the problem to work out, but nevertheless, I don't want to just simply say this is going to be the solution without actually have like not verifying it, mathematically speaking, which is what I'm doing right now. All right, so this 133, let's it repeat itself anywhere. And so another key thing here, guys, is that the order of these indices is important. So when I call out numbers like 133, what I'm basically saying is I'm taking the partial derivative of the 1th component, which if we're thinking about our space-time, the 1 component is going to be our x component. So I'm taking the partial derivative with respect to our x component of the element that's at the 3, 3 position of our matrix H, which is our perturbation matrix. So Tanner, you're new, so I have to explain this actually. So the idea here is that if you could imagine me and you holding a sheet, like a bed sheet, that bed sheet would represent space-time. So in space-time, we have 4 coordinates. We have a temporal coordinate, well, 1 temporal coordinate, and we have 3 spatial coordinates. And so this sheet represents our space-time, which is composed of these coordinates. And the idea is that if we want to be able to identify the distance between 2 locations on our sheet, we have to establish a mathematical equation that will look very similar to Pythagorean's theorem. And this equation would be known as the metric. And so in the case of a flat space-time, which is what our sheet represents because it's flat, the metric is going to be negative c squared times dt squared. And if you make that positive, the temporal coordinate, all the spatial coordinates must be negative. So you get negative dx squared, negative dy squared, negative dz squared. And this equation, which it resembles the Pythagorean theorem, will give us the distance between 2 points times that particular thing squared. Excuse me. So now if you imagine if we take our sheet, right, now that we've established how to define distances between 2 things, if we take our sheet and we start placing masses at random points on our sheet, well, the sheet's no longer flat. It's no longer a flat space-time. It now will have curvature at the points where the masses are located. And so we have to now be able to modify how we define distances between things, right? And so to make that modification, we basically would take our flat space-time metric and we would add on to it what we can call a perturbation matrix or a perturbation metric. In this case, our perturbation metric is represented by these H terms we're seeing here. And so essentially what's going on here in this particular problem that we're working on right now is that we're taking the partial derivatives of the elements within our perturbation matrix. There's more to it, but hopefully what I just said will kind of make sense to some extent and give a little bit of background on what we're doing here with all these H's here. So again, we're still looking for terms to like cancel out. All right, so 133. I think I end up establishing that 133 is unique and that it will not cancel out. 133 times 133. Okay, so 311. I think that is also unique. No need to worry about it. 211. 211 is not unique. It shows up in two places. It shows up on the second line here as the last term. Or 211, 211, excuse me. And it also shows up again on the 1, 2, 3, 4, 5, 6, the seventh line, first term. And so on the seventh line, first term, it's positive because the two negative signs end up becoming a positive. On the second line, it's negative, so it goes away. So the second term of the second line goes away. So 1, 2, second term is here. It's going bye-bye. And I believe I said the seventh line. So 1, 2, 3, 4, 5, 6, 7. The seventh line, first term. 1, 2, 3, 4, 5, 6, 7. First term. 211, 211. And so this now goes away as well. Modification made. And it goes. 222, 222 is, or no, 122, 122 is that unique. That's unique. A unique element, so we leave it alone. 122, 211. I think that's good as well. 111, 111. That is not unique. And so actually I think there's a trend going on here. I just haven't like stated it. So that is, let's see. It's positive here. Or is it positive in both places? No, that can't be right. Did I make a mistake? Huh. So based off of this, I mean, it looks like it would add together. They wouldn't cancel. Which is kind of weird to me because I was expecting things to cancel out. And this could definitely be one of those situations where I've probably like messed up a sign or something like that. Let me go ahead and verify it really quick. So the way in which I can verify this is by going back to the terms Um, going back a little bit and just verifying that that particular term should be what it is. And so what was it again? I think it was I was looking at the was the 111. No, 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 no. I think that's right actually. The only time the one no, that's not right. That's impossible. 111 can't be negative. All right, so let me explain what's going on in my head here. I'm looking at the subscripts on the terms, and I'm thinking about the corresponding Christoffel symbol. And whenever you have a Christoffel symbol, like for example, the Christoffel symbol of superscript 1, subscript 1, 1, the value that you'd produce from that, at least with this particular problem, or given the nature of this problem, should be positive because of the fact that, well, one, the contravariant metric G superscript 1, 1 is going to be positive. And so that positive value multiplied times the sum of the partial differential equations of the Christoffel symbol, which will all basically just cycle through 1, 1, 1. There's three terms in that. The last two terms are going to cancel out because one is positive, one is negative. And the first, so I've made a mistake somewhere else. Again, guys, like I said, like keeping track of all these negative signs is difficult. And we can actually verify this really quick. So I can go back to scene 2. And what I'm going to do is I'm just going to scroll to where I'm going to scroll to where I've defined all the Christoffel symbols. And if I'm not mistaken, it should be a positive value for the Christoffel symbol 1, 1, 1. Yep, it should be positive, which is right here. So the fact that it's negative and that other one is not right. Oops, I did not mean to do that. Sorry, guys. And I'm realizing I'm just talking here, guys, and unless like you've done this before, a lot of the stuff I'm probably saying is like just gibberish. But to kind of break down what I mean, because I don't want you guys to not understand what I'm saying here. Um, hmm. Let's see. What's the best way of doing that? What we're going to do is we're going to scroll down and we're going to look at the definition of the Christoffel symbol, so you can kind of understand what I'm saying. Right here. So if you notice, if you look inside the parentheses here, you basically cycle through JKM, KMJ, MJK. In our case, all of these variables J, K, and M are equal to 1. So you're basically getting the exact same partial differential equation or partial derivative. You're going to get partial of 1 G sub 1 1 plus partial of 1 G sub 1 1 minus partial of 1 G sub 1 1. Given that they're all the same, the last two terms will cancel. They'll equal 0, only leaving you with the positive partial of 1 G sub 1 1. And that's, of course, going to be multiplied times G superscript 1 1 times a half. And so that's the reason why the fact that I've seen it be negative in the other PDF, I know it must be wrong. And I have to make the correction. I realized I just completely walked away from chat on Slack, and so let me see. I've also see that I've lost some people too, maybe. This is definitely something I probably should have done like in my off time and gotten all this math worked out. But then again, It's a good experience to be able to see, what graduate students have to go through. All right, this is the one I want to be at. I'm going to minimize that. And so that means I need to scroll up top and see what did I do wrong here for it to come out negative. And it's here. Should that term be 1, 1? It should be 1, 1, 1. All right. So term 4, the sixth term of term 4. That's the sixth component of term 4. Where is that negative sign at? Here. So fix that. Let's typeset it. All right, that should fix that. And I also have to fix it down here as well. But nevertheless, the term should cancel out because one term is positive and one term is negative with that fix. So we can get rid of that line altogether. Here, this is to make sure I'm deleting the appropriate thing here. That goes away. And its corresponding term goes away down here. 1, 1, 1. That goes away. Typeset it. And we reduced the terms a little bit more. And I think the last one I was left with was not 1, 2, 2, but I think it was 1, 0, 0. And I think we already verified that the 1, 0, 0, 1, 0, 0 term is unique. And so that's it, guys. I think that's it for this particular portion of it all. I'm not even going to try to mess with this. We're going to just move on and just pray and hope that I saw them all. This is interesting, actually. Partial 1, 3, 3. All right. So the next thing to do, of course, is now to bring all the terms of this particular Ricci curvature tensor element together. I'm trying my best to be very careful in how I'm saying this stuff, but so let's just do this. Let's copy and paste this line. And let's just go ahead and put the terms together. And so I can delete this. And so the very first term was defined here in this last line. The next term is defined here. And then the very last term, we just kind of like solved for, which is a combination of two things. see what it looks like. I can fix that by doing this. And hopefully everything will line up now. All right. And so looking at the second order partial differential equations, which are basically summarized in these first two terms up top. I'm not seeing any cancellation there, am I? I guess on that 1, 1, 1 second order partial differential equation there might be cancellation. No, there. Oh wait, I didn't do that right. That should be a negative sign. That's being subtracted, so there is cancellation. So it looks to be that the first component of the first term. Hopefully that makes sense. The negative partial superscript 2 subscript 1 h11. That one gets canceled out with the second component of the second element. This is all right. So I can just delete that 1, 1, 1. That goes away. Oh wait, let's see. I got a question here. So Peter is asking. So in this model, is distance between 2 points on the sheet always measured in 3D space? So distance for what we're talking about here is measured in 3D space with a temporal component as well. And so to kind of explain what I'm saying here, we're going to quickly go over to the internet. So let's do this. Internet, we need you back. So I'm going to go ahead and load up a internet browser. Okay, and we're going to move this up and bring me back. All right. And so, oh wait, internet, how big is, okay, perfect. So what we're going to type in now is Minkowski space, Minkowski space. Let's see if we can. Oh, that was Ed Tanner. Okay, good question, Tanner. So yeah, the distance between 2 points is essentially defined by, let's see if I can find a good. This looks good. Let's go with this one. The distance between 2 points is going to be defined by this metric, where you're considering, if you were to consider two events that happen within this space-time, that event, of course, could have a time stamp to it, so it can occur at some time, and it could occur at a particular position also. So if you want to be able to determine the distance between these events, because the events, of course, can either happen in time, happen or changes in time, changes in space, or both. You can determine that distance using the metric for that space time, which for a flat space time the metric is going to be the Minkowski metric. And so for a flat space-time, we get essentially this equation we see here. Where if you notice the temporal coordinate is its sign is different relative to the three spatial coordinates. So have I missed? Okay. So yeah, Peter's showing me some stuff here. Twitch's chat, yeah, it's sucking today. Oh, perfect. Have you taken General Relativity, Tanner? Because I don't know what other courses. Ah, so this shows up in statistics. Hmm. Honestly, I wouldn't. Well, partial differential equations aren't really that much different. Well, at least in my opinion, aren't really that much different from your ordinary differential equations. For the most part, same rules apply. But yeah, the only time I could think of actually having to worry about these metrics would be in like yeah math course. Other than like in physics in general relativity. All right. Oh wow, it's 103. I didn't even notice. All right, guys. This is what I'm gonna do. This is what I'm gonna do because I'm realizing, of course, like this is it's if you're currently in general relativity and you're viewing this stream, then this might be helpful. If you haven't already, of course, like learned it. But I'm going to go ahead and solve for all this, and in the next stream, we're going to like bring it to an end and see what the solution should be. And I mean, I feel confident that the track we're on, the path we're on now is good. So, well, guys, thank you for coming to today's stream. I definitely had a lot of fun with it. I didn't get as far as I would have liked, but definitely had fun. I hope you guys had fun too, even with the whole issue of the chat failing us. Hopefully that is not a issue with the next stream. I can't see you guys saying like bye and stuff like that. So, oh wait, hold on. The chat's back. Really? Oh, that is just weird. Did everyone see me type that? So, oh yeah, I forgot to mention, of course. Um, to better answer your question, actually, Tanner, I guess a better way of imagining it is you take your sheet. The sheet does represent it would represent four-dimensional space, which is kind of weird because the sheet is like 2D. But maybe an easier way of thinking of it is that every single point on the sheet is a single element in a 4D space. So every single point is unique. If you want, you can imagine sheets stacked on top of each other, actually, where a single sheet is at one instance of time. However, it spans over all the spatial coordinates. Or you could think of that single sheet. Yeah, it's yeah. I'm just gonna finish with the problem in the next stream. Yes, yes. So exactly, when you put mass on the sheet, you've now changed the space time. It's no longer a flat space time. It can no longer be defined by the equation we're seeing right now in the background. We have to modify this equation to account for those changes due to now that you have mass within your space time. Yep, that's exactly how you should picture it. The curvature of space time changes due to mass. You move from a flat space time to now a curved space time. Oh, that's right. Astronomy Cast is going to be going down in like an hour time. So, guys, thank you for coming to today's stream. I will spend some time in actually like solving the rest of the scalar curvature, and then we'll just like dive directly into like the solution when I return on next Wednesday at 12 p.m. Central Time. All right, guys, thank you again for coming by, and I will talk to you guys later. Bye.